In this video, I will explain a new type of space-based X-ray telescope. The first telescopes of this kind are beginning to be launched now and in the near future. Everything from radio waves, the light which you are using to watch this video, through to X-rays and gamma rays is part of the electromagnetic spectrum. Astronomers record these waves to observe the universe around us with radio dishes, microwave antennas, telescopes on Earth, in space, and many other devices. Seeing the universe through X-rays and gamma rays is challenging, however. For a start, they are strongly absorbed by our atmosphere and hence they do not reach the ground. And a good thing too, because these are dangerous forms of ionizing radiation, very hazardous to life. These short wavelength, high energy rays can therefore only be observed from orbit. The other major challenge is to create an optic which will focus these types of waves. I have made a video about how optics work, link on the screen and in the description, but to summarize, an optic is a device which takes rays spreading out from a distant point of light and focuses them to a point on a detector. The three most common types are pinhole cameras, reflecting telescopes, and lenses. A pinhole would work for very intense X-ray sources, such as experiments in plasma physics, but not for faint, distant astrophysical objects. For X-rays and gamma rays, there is no material which can refract them sufficiently to form a lens, nor reflect them sufficiently in the usual way to form a reflecting telescope such as the Hubble. For X-rays there is a hope. They can be focused by reflection, but only with so-called grazing incidents, where the ray comes in almost parallel to the surface of the mirror and its path is deflected by a very slight amount. The simplest solution is to create a cylindrical optic. The X-rays are reflected inwards at grazing incidents by the inside of the cylinder, which is polished and coated with gold. To improve on this basic design, the cylinder can be tapered to resemble part of a parabola. Additional cylinders, some nested inside others, are added to greatly increase the number of rays being focused and improve the quality of the image. This is the type of optic inside NASA's Chandra X-ray Observatory mission, which has been collecting valuable astronomical data for decades. The disadvantages of this type of telescope are a relatively small field of view and, a big deal for space applications, very large size and mass. Nature has provided a solution to both these problems. Species of lobster have evolved optics in their eyes to focus light by grazing incidence reflection. Instead of several larger mirrors, a lobster eye contains millions of microscopic channels. Each of these square channels collects and reflects the light down to the photosensitive cells of the lobster. Versions of these lobster eyes can be artificially manufactured to reflect X-rays. Many glass structures resembling square optical fibers are made and bundled together while the glass is hot. The cores of the fibers are then chemically etched away to create an array of so-called microchannels. This optic, initially flat, is slumped onto a sphere to make it resemble and function like the eye of a lobster. Finally, the inside of the microchannels is coated with the metal iridium to increase its ability to reflect X-rays. The coating is applied by evaporating the metal in a vacuum chamber and letting it condense into a thin layer on the glass. The final product has channels typically 20 to 40 micrometers or millionths of a meter wide, the walls between them 5 to 10 micrometers wide. Note that a human hair is about twice as wide as this. Overall, the optics are up to a few millimeters thick, making each one a very light piece of glass, which is advantageous for space missions. Though it might sound as if they are very thin, these optics have been demonstrated to comfortably survive the bumpy ride of a typical launch to orbit, fully intact. Let's look at what happens to light approaching the optic from a single point source like a distant star. On the left, I will show the view of the microchannel, where the photons impact, and the intensity of photons arriving at the detector. On the right, I will show a cutaway side view and the paths of photons. Some photons pass straight through the grid of microchannels without being reflected or focused in any way. When impacting the detector, these straight-through rays are spread out uniformly, and as a result, they are not very intense. Some rays graze the upper face of the microchannel and are reflected downwards to the detector. Similarly, some graze the bottom face and are reflected upwards. Rays from both these mirrors converge at the same height on the detector, but because they haven't been focused at all in the side-to-side direction, they are spread out horizontally. These types of rays therefore show up on the detector as a horizontal bar of moderate intensity. Correspondingly, some rays are reflected by the two vertical faces and form a vertical bar on the detector. Finally, some rays arrive in the corner to be reflected by a vertical and then horizontal face, or vice versa. These doubly reflected rays pass diagonally to the center of the detector, forming a very intense focal spot. Overall then, the lobster eye focuses light from a single point to a focal spot, as any good optic must do. In addition to the central spot, a cross-shaped feature is also produced. This is not ideal, but as we will see later, this will produce high-quality images of scientific phenomena. One advantage the lobster has is that its eyes have a great field of view, allowing it to see things all around. The overall shape of the focusing microchannels is a part of a sphere of given radius, while the light is focused to a concentric sphere at half the radius. For an artificial lobster eye, the angle can be as large or as little as required, up to a full sphere, in which case the optic would gather light from all directions simultaneously. An all-sky lobster eye X-ray imager has even been proposed for the International Space Station, which would do exactly that. In practice, given the lack of demand otherwise, no spherical X-ray detectors have been designed or manufactured. At present, flat detectors must be used to merely approximate part of the detector sphere. Incidentally, X-ray detectors are souped-up versions of silicon CCDs, charge-coupled devices, like those you have in your cell phone or digital camera. Also, it is difficult to construct a whole telescope out of a single glass piece, so smaller individual micropore optics are mounted onto solid struts to create the final instrument. These features give lobster eye telescopes a wide field of view while keeping them compact. Rather than being 10 meters in length, as is the Chandra telescope, lobster eye telescopes can be under a meter. All types of grazing reflection telescopes must have open apertures, which are the microchannels in the case of the lobster eyes. We have seen already how they let in straight-through X-rays, but they will also allow in other wavelengths of light and radiation in the form of fast-moving charged particles. This would saturate or damage the detector. In order to block out visible and ultraviolet light, a thin layer of aluminum is deposited over the top. This layer does not stop the X-rays, but it is largely opaque to other waves. To protect the telescope from high-energy electrons, magnets have been installed at the supporting struts to create a web-like field over the telescope, as reported by a rather handsome fellow, if I may say. The very first space mission is the Chinese Longxia Yan 1, or Lobster Eye X-ray Exploration Satellite 1. This is reportedly a joint project by Nanjing and Hong Kong universities. There are few peer-reviewed papers about the mission, but with a launch mass of just 50 kilograms, this appears to be more of a technology demonstration than observing a particular scientific phenomenon. The first full science mission to be equipped with a lobster eye X-ray telescope is called SVOM, or the Space-Based Multiband Astronomical Variable Objects Monitor. This is a joint French-Chinese mission, although the lobster eye telescope was assembled at the University of Leicester in the United Kingdom. The variable objects to which the name refers are gamma-ray bursts, violent astrophysical events occurring in distant galaxies. In a brief moment, a huge amount of energy is released in an explosion which outshines its host galaxy. Many gamma-ray bursts are the mergers of pairs of black holes or neutron stars. As these very massive objects spiral towards each other, they produce gravitational waves. In fact, different detectors have simultaneously recorded gravitational and electromagnetic waves arriving from the same event. This means that the gravitational waves must have traveled at precisely the speed of light, which in turn tells us a lot about how gravity works fundamentally. Another interesting reason to study gamma-ray bursts is that a huge proportion of the heavy chemical elements on Earth, gold, lead, uranium and so on, were synthesized in the mergers of neutron stars, as shown in this graphic. Fusion and other nuclear processes in stars ordinarily do not result in elements much heavier than iron, but the capture of neutrons in these events causes nuclei to become massive. The SVOM mission will detect and study gamma-ray bursts through a number of electromagnetic waves. The two types of gamma-ray detectors will first pick up an event, a lobster eye telescope will pinpoint it more finely, a conventional telescope will also pick up visible light from the event. The SVOM satellite will quickly communicate the exact location of the gamma-ray burst in space to a network of Earth-based observers. Here is a hypothetical example of how this will work. Gamma rays are even harder to work with than X-rays. As a result, the gamma-ray detectors are not particularly accurate. When they detect a gamma-ray burst, these detectors can localize it to an angular size in the sky approximately that of the Messier 4 globular cluster. This group of stars itself is practically in our galactic backyard and unlikely to be the source of a gamma-ray burst. However, let's imagine that a gamma-ray burst did happen in the general direction of Messier 4, albeit in a galaxy far beyond it. The gamma-ray detectors would flag up an event in a region of about this kind of size. This is too large a portion of sky to search through by conventional telescopes. Fortunately, the mission's Lobster Eye telescope will pick up X-rays in the characteristic cross shape we have seen already. The gamma-ray burst would therefore be localized to the focal spot at the center of the cross. The visible telescope on board the satellite, as well as others on the ground, can then target this precise part of the sky. X-ray telescopes can also discriminate the exact wavelengths of the rays they are receiving, which is important scientifically. For example, visible light from the sun is yellowish, meaning that there are more photons with longer yellow wavelengths than shorter violet wavelengths. The proportions give us insights into the sun. Similarly, measuring the wavelengths of X-rays from gamma-ray bursts will provide lots of useful data about their physics. Another mission which will use a Lobster Eye telescope in a very different way is SMILE, the Solar Wind Magnetosphere-Ionosphere Link Explorer. This is a joint mission between the European Space Agency and the Chinese Academy of Sciences, though again, its Lobster Eye telescope will be assembled at the University of Leicester, England. The solar wind is a flow of plasma out from the Sun into the wider solar system. The protective magnetic field of the Earth cuts through this flow like the bow of a ship, forming a buildup of plasma in front of it. Plasma enters the Earth's magnetic field through polar cusps above the poles, from where these charged particles stream in to cause the auroras. Just as the weather around sea level varies daily, so too does space weather in the ionosphere. This in turn has major effects on our economically vital satellite infrastructure. A global effort is underway to understand space weather, of which SMILE will be an important part. SMILE will use a Lobster Eye telescope to image the bow shock and polar cusps. The plasma in these locations is a relatively strong source of X-rays. Oxygen ions, for example, emit characteristic X-ray wavelengths. The satellite will orbit in a highly elliptical manner, allowing it to spend a long time observing the Earth and its magnetosphere from a distance. The large field of view available to a Lobster Eye optic will allow the very large regions of plasma to be imaged at once. Here is how SMILE might image the Earth's bow shock. On the left is a simulation of where the regions of plasma are around the Earth. The redder colors mean more plasma, emitting more X-rays. Suppose this simulation is accurate. Once those X-rays get focused by the Lobster Eye and each point source creates this kind of cross which I showed before, the detector will record something like the image in the middle. Grainy, but very reasonable. Electronic processing techniques can then reconstruct the image on the right, which is a good representation of reality. This means that whatever the conditions are like in space, SMILE will be able to record them. Also aboard this spacecraft will be an ultraviolet optic, a sensor to collect hydrogen and helium ions, and a probe to record the magnetic field in its present location. All of these sensors together will help build up a scientific picture of the plasma and magnetic field around the Earth, which in turn will improve our understanding of space weather. Thank you for watching. Look out for more information about the space missions I have talked about in the future and any other scientific missions which use Lobster Eye telescopes.